Okay, here we are on page 2 of the HL Vector Apps Addendum, section 15C. Let's recall the vector equation of a 3D line. Just to spark your memory, here is the parametric equations for a 3D line. And we can easily change this into a vector equation just by grouping the XYZ into a vector, grouping A1, A2, A3 into a position vector, and grouping B1, B2, B3 into a velocity vector or a direction vector, and then multiply the direction vector or the velocity vector by lambda, okay, which is called the parameter. All right. By equating the lambda values for each one of these three parametric equations, we could solve for the lambda and equate them. You end up with this. And just to show you how that works, I'm going to show you how to do it with the first one. So if you have x equals a1 plus lambda b1, you can solve for lambda by doing x minus a1 equals lambda b1, and then dividing both sides by b1, so then you end up with lambda equals x minus a1 divided by b1, and now you can kind of see why the first expression looks like that. Okay, so you just do a similar process with each one of these, and then you set them equal to each other, and then you make kind of like a giant equation, which is a Cartesian equation to define a three-dimensional line. Okay. Now we're going to do problem 5e, which is to describe like this line. Use let's see. We want a line perpendicular to the XOY plane. What is the XOY plane? Well, just to draw you a picture of it, you don't have to draw a picture, but if you were going to draw a picture, it looks like a plane which sits both on the x-axis and the y-axis, thus the name XOY plane, okay? So it kind of looks like that. And they say a line perpendicular to the XOY plane, which would, you can see now that a line perpendicular to the XOY plane would be a line that is parallel to the z-axis, right? So this line that's parallel to the z-axis would emerge from the XOY plane at the position x equals 3, y equals 2. It would be somewhere around here, okay? And, of course, then it would go through 3, 2, comma, negative 1. In fact, it would go through 3, 2, comma, any point, any third coordinate, okay? And sorry that I messed up this PDF, but actually we're supposed to find this line with three types of equations: vector equation, parametric equation, and Cartesian equation. So let's start with vector equation. That's kind of the easiest one. So I'm going to make a equation of a line in 3 dimensions. It's going to be x, y, z equals, and then I'm going to put this as the position vector because one of the points that we want to go through is 3, 2, comma, negative 1. So we're going to put that there. And then knowing that the vector is going parallel to the z-axis, then the direction vector would look something like this: 0, 0, 1, or 0, 0, negative 1, or 0, 0, something, okay? And then put lambda there. So that's the vector equation for the line which goes through this point and is parallel to the z-axis. And of course, you could do parametric equations by separating each one of these layers out, and 3 plus 0 lambda would just be x equals 3, right? And y equals 2 times 0 lambda would just be y equals 2, and finally z equals negative 1 plus lambda would be the only equation that really has a variable in it, okay? And so that is the parametric equations. And then finally, we would have the Cartesian equations. Remember that the Cartesian equations don't have lambda in them. So this z equation, we don't have that for the Cartesian equation. Otherwise, we use the other two equations, which are x equals 3 and y equals 2, to define our Cartesian equation. Okay, just with those two, we know that z can be anything, so we don't need to actually specify that for the Cartesian equation. We just say x equals 3, y equals 2. Okay, now for number 9. The parametric equations of a line are blah, 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 for lambda is a real number. Find the coordinates of the point on the line corresponding to lambda equals 0. Okay, that's not too hard, okay? I'm just going to rewrite it as a vector equation because I think vector equations are a little bit easier to handle than the Cartesian equations because you don't have all these separate system of equations. You just have just a one giant one. So I'm putting L, M, N for the vector that's multiplied times lambda. Now, the coordinates of the point on the line corresponding to lambda equals 0. Now, imagine if you put 0 in for lambda, what's going to happen? So the answer to A would be x0, y0, z0. Okay? And then the direction vector of the line would be this vector here, which is L, M, N. And to write the Cartesian coordinate equation of the line, what you can do is you can first separate out the parameters and solve for lambda. So that would be x minus x naught divided by L is one of the lambdas. Another one would be y minus y naught. When you have a little zero like that, you say why not? Why not? M. And the last one would be z minus z0 divided by n. Okay, so there is the Cartesian equation for the line. Just ignore the lambda that I stuck in there, okay? All right, number 11. The perpendicular from a point to a line minimizes the distance from the point to that line. Use quadratic theory to find the coordinates of the foot of the perpendicular. Remember that the foot of the perpendicular is the point where, like let's say this is the point and this is your line. If you want to find the shortest distance between the point and the line, and draw an imaginary line between the point and the line, and the place where they intersect, this imaginary line intersects the line L, is the foot. Okay. So the point is going to be 1, 1, 2. And the equations for the line are these equations here. And so one thing that we should do is we should figure out the direction vector of the line. Okay? One way to figure out the direction vector of the line is to arrange it in vector form first. So we're going to have x, y, z, where I'm going to arrange the parametric equation in the vector form. So I'm going to have 1, 2, 3 plus lambda times 1, negative 1, 1, right? Because this has 1, negative 1, and 1, right? All right. Now, so the direction vector is 1, negative 1, 1. So let's say that the foot of the perpendicular is an unknown point, so we're going to call it x, y, z. Okay? So one thing I do know is that the direction vector of the line, which is 1, negative 1, 1, is perpendicular to the vector between P and the foot. And the vector from P to the foot is, I could write that as x, y, z minus 1, minus 1, minus 2. So if I take the P point and subtract it from the foot point, that gives me that expression there, okay? And then I'm going to scalar product with 1, negative 1, 1, and that should give me 0, okay, because they should be perpendicular to each other. Okay, so normally one of the ways you might do this is to do the scalar product and then also use this equation to figure out what the value of lambda is that would make this 0, okay? But it tells us to use quadratic theory this time. So how about if we figure out what the distance is between the point and the line. So basically what we're doing is we're figuring out the distance between 1, 1, 2 and xyz. And instead of putting in xyz, I'm going to actually put in the parametric equation forms of xyz. And that would be the vector, p to the foot, which would be 1 plus lambda, 2 minus lambda, and 3 plus lambda for the xyz coordinates. And then I'm going to subtract off the p coordinates, and that gives me a vector expression for p to the foot. Okay, and I can find the distance or the length of this vector by doing, let's see, 1 minus 1 is 0. So the first coordinate, the first component will be just lambda. The second component will be 2 minus 1, 1 minus lambda. And the third component would be 1 plus lambda, right? And so I could figure out the length of this p to the foot vector, and it would be lambda squared plus 1 minus lambda squared plus 1 plus lambda squared. And basically, I want to minimize this distance. Okay, right? Because I'm trying to find where the foot is. So that would be the square root of lambda squared plus 1 minus 2 lambda plus lambda squared plus 1 plus 2 lambda plus lambda squared. And let's see, if I want to simplify that, there would be lambda squared, lambda squared, lambda squared in 3 places. And then minus 2 lambda plus 2 lambda cancels out. And then plus 1 and plus 1 add together. So then I would end up with plus 1. Or plus 2, right? Okay. And this would be minimized. So how do we minimize that? Well, 3 lambda squared, if we're going to minimize the square root value, we're actually just going to minimize the value inside the square root. So as long as we minimize 3 lambda squared plus 2, we will be minimizing the square root value too. So to minimize the parabola 3 lambda squared plus 2, the smallest value, the value of lambda which would make it smallest, would be lambda equals 0. And we know that because 3 lambda squared plus 2 is a parabola that is centered at x equals 0, right? The axis of symmetry is at 0. So that means the lowest value or the minimum value would be at lambda equals 0. If we know that lambda equals 0, then we could find the values for x, y, z easily, right? If you put 0 here, then basically the values for x, y, z are just 1, 2, and 3. So it turns out that the foot of the perpendicular is just going to be the coordinates 1, 2, 3. Okay?